G'day guys, and welcome to our lesson on gravity. Now there are four principal forces acting in the universe that we know of. There's the strong nuclear force, the weak nuclear force, the electromagnetic force, and then there's gravity. And the force of gravity is basically the force that attracts any two bits of matter in the universe towards each other. If we were to look at the solar system, we'd see gravity at work. And this is because gravity is very significant when there's either large masses involved or large distances, because it can act over very large distances compared to the other forces. So let's look at the solar system, and let's see if we can identify some of the clues that tell us that gravity is acting there. Now the first clue is that instead of having matter evenly distributed across the whole solar system, you have matter packaged into these discrete little planets, or where 0.9% of the matter is in the sun. So we think, how did that matter come to be packaged like that? It must have been attracted to itself. Then the next clue, the actual shape of these packages is spherical. And the spherical shape is the ideal shape that matter makes when it's trying to attract every other bit of matter in its locale. And finally, the third major clue is this. This is what Galileo saw. We know from circular motion, if you want an object to move in a circle, there has to be some kind of centripetal force keeping that object moving in that circle. And since all the planets do in fact orbit the sun, there must be a force on each of these planets acting towards the sun. And therefore you see that the matter is, in a way, attracting itself. So in order to know exactly how big that force was, that little green arrow I just drew, we use this formula here. The force of gravity is equal to the gravitational constant. That never changes. It's like the spring constant in a way, but there's only one gravitational constant for the universe, multiplied by the mass of one object we're talking about, multiplied by the mass of the second object we're talking about, divided by r squared, where r is the distance between the centers of those two objects. So I'll draw it down here. This is the mass of object 1, this is the mass of object 2, and this here is r. And the forces we're seeing would look like this. Fg is equal to g times m divided by r squared. I'll pop in an arrow there. And that is the force of this mass on this mass here. Now if you were to ask the force of this mass on this mass, you get an equal arrow in the opposite direction. And that obeys Newton's third law: for every action there is an equal and opposite reaction. Now just because the size of these forces, Fg, and we'll say this is negative Fg, is the same, does not indicate that these objects will accelerate towards each other with the same acceleration. Because we know that force is equal to mass times acceleration, and force over mass equals acceleration, the mass here with the smaller mass is going to accelerate faster, because when this term becomes smaller, this term becomes bigger. So let's figure out, instead of just drawing these yellow arrows and going off size, let's figure out the exact magnitude of the gravitational force between the moon and the Earth. So the mass of the Earth is this: 5.97 times 10 to the 24 kilograms. And the mass of the moon, m, is equal to around 7.35 times 10 to the 22. So these are just approximations, but they're fairly good ones. And of course the gravitational constant is here, and the distance between the center of the Earth and the center of the moon I have here, r is equal to 3.84 times 10 to the 5 meters. Notice the units, kilograms and meters. That's what you want to be working in whenever you're using these formulae. So the exact force of gravity here, Fg, is equal to g m on r squared. That becomes 6.67 times 10 to the negative 11 multiplied by 5.97 times 10 to the 24 multiplied by 7.35 times 10 to the 22 all over 3.84 times 10 to the 5, and if you're on your calculator, make sure you get those brackets in, squared, which comes out to a total of, I have 1.98 times 10 to the 26 newtons. So this is the force between the moon and the earth. Let's talk a bit about proportionality. If I double the radius here, this becomes times 2, and since it's squared, the bottom actually becomes times 4. So the bottom terms becomes times 4, and therefore the force drops by a factor of 4. And if I halve the radius, it becomes r on 2 squared, which is another way of writing 1 on 4 r squared. So it's become 4 times, because this 4 jumps up here. It's become 4 times the original force. So double the distance, quarter the force, halve the distance, quadruple the force. Let's figure out also why we use G equals 9.8. Well, actually in physics we use 10. That's right. If we have an object sitting on the surface of the earth, we say, hey, it's got a weight force of mg, and we say G is equal to 10. And in specialist maths, you'd say G is equal to 9.8. That's a better approximation. Let's prove this is a good approximation for figuring out the weight force of an object. So say I've got an object sitting on the surface of the earth there. The mass of the earth hasn't changed. It's still 5.97 times 10 to the 24. G hasn't changed, but certainly the distance between the center of these two objects has changed. It's actually the radius of the earth, which is, I have here 6.37 times 10 to the 6. Now we know that the force of this object on this object is given by this formula. So F G is equal to G M on R squared, which becomes 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 all over 6.37 times 10 to the 6 squared multiplied by m. We haven't said what the mass of this object is yet. And this comes down to, if you plug that into your calculator, I'll do it now just to check, 6.67 times 10 to the negative 11 multiplied by 5.97 10 to the 24 divided by bracket 6.37 times 10 to the 6 all squared. Whoops, did I say 5.6? I meant 5.97 here. At least I've written it right. And that comes down to approximately 9.81 times m. So our assumption that G is round about equal to 10 is based on this idea that the force of an object sitting on the Earth's surface, the force on that object exerted by the Earth is around 9.81 multiplied by the mass. That's the justification for that value of G. In physics, gravity is often tested in conjunction with circular motion because, as we said before, all these planets are orbiting the Sun, and orbits are a very specific case where the gravitational force is equal to the centripetal force. So look out for that in future lessons.